Okay, welcome back. Today we're looking at the last part of question 1 from the 2018 MAT paper. And we are shown 4 different graphs, A, B, C and D. And we are asked to work out which of these graphs could be generated by the equation p of x plus p of y equals 0 for p a random polynomial. So we need to work one by one, work out which of these could possibly be generated by any polynomial. And we're given a few different combinations down below. Okay, so here we have 4 very rough sketches of the graphs we were shown in the question, A, B, C and D. And this is the equation we were told, so p of x plus p of y equals 0 for some polynomial p. What's really important to observe is this has to be the same polynomial. So we can't just take some polynomial of x and then a different polynomial y. These have to be the same polynomials. So if we consider the first graph, this is a parabola. So this is going to be the form, this is for part A, this is going to be of the form y equals alpha x squared plus beta x plus constant gamma, for example. So what's really important is that the powers of the 2 variables, x and y, they're going to be different. So alpha has to be non-zero to get this shape. So we're going to have a polynomial. If we wanted this to be true, we'd need a polynomial in terms of x that has highest order 2 and a polynomial in terms of y that has highest order 1. And that's not possible if we want the same polynomial. So that tells us we can immediately rule out A. This cannot be generated by this equation just because the polynomials would have to have different orders in the variables. So let's do another easy one. Let's look at D. This is a straight line. And this can be generated by this equation because straight line is typically of the form y equals mx plus c. So we'd have, let me just write that out, y equals mx plus c. So we see that both these powers of x and y are the same. So this leads us to think we can generate this graph, and we can actually do this if we take the polynomial p of x equals x. So then we have x plus y equals 0, or y equals minus x, which is exactly what we're seeing. We're seeing the straight line y equals minus x, which is the same as y equals x, just reflected about either axis. So that means we can do this one. So that is one of the correct answers. We can also look at C. So this is a circle. This is a bit easier than that one. We'll get to that in a second. So C, this is a circle, so it's always going to be of the form x squared plus y squared equals a constant, c squared, for example. So we also see that the powers of x and y are the same, so this leads us to think we can generate this graph from a polynomial. And we can take p of x equals x squared. So that should, well, actually we need a constant as well. So if we take p of x equals x squared, we get the x squared and we get the y squared. To get this constant, we can just take c squared over 2, minus c squared over 2. So when we add both of p of x plus p of y, we get x squared plus y squared minus c squared. And then setting equal to 0, we can just swap the c squared onto the other side. So that is how to generate a circle just with the same polynomial. So C is another solution. And the final part of this question is to look at B. So B should be ringing alarm bells already because we have these very sharp corners. And this is definitely not something a polynomial can generate. So there's a few reasons you might see this. A polynomial is always differentiable. So how would we define a derivative at these points? We can't really do that because if we look from the left side, then maybe the tangent is this line. But if we look from the other side, maybe the tangent is this line. So we're never going to be able to define a derivative at this point. And that is something that polynomials cannot satisfy. So polynomials are always differentiable, and we're never going to get these sharp edges in any diagram like this. So another way to see that, if you don't see the differentiability, we can consider just a region of this graph. So we have these piecewise constant lines. So if we look at this region here, where y is constant, let's say y takes value a. So in this region, x varies between some interval and y is constant. So we can just think about this equation as p of x equals minus a. But this is true for an interval of x, which means that the polynomial is going to have to be constant. So p is constant. We cannot have a polynomial that is constant in an interval and that it is not constant. That just breaks the laws of what it means to be a polynomial. And if we have a polynomial that's constant, then this equation reduces to a constant on the left-hand side and 0 on the right-hand side. And this is either always true if the constant is 0, or it's never true if the constant's never 0. So we'd only get a diagram that's either covered with dots, with solutions, or has no solutions, which is definitely not what we're seeing. So that is another way to see that this cannot be generated by this equation. So graph B is not a solution. So just to summarize, we've shown that A and B cannot be generated by this equation, but C and D can be. And that is the end of question 1.